Okay, now I looked at the function. I guess I have a couple of comments here. One thing is my arithmetic was wrong, so there may still be some problem with it. So I need you to check, and that's the main thing. Now, one thing I should say is that here you had two sections. What's going on here? What's down here? Yes, you had two sections, one for the inverse and one for the non-inverse. You can combine them this way because you can change these parameters in the function without changing them outside. So you might as well just replace the parameters with the values that are appropriate for the inverse function and then just use that. I think I changed the equations here a little bit, but you will check. All right. So what we'll have to do here is to check it, what we want to do is we want to apply the rescale function to the function h. We want to apply that rescale Gauss to the paraminit and make sure that it makes sense. And so to do that, I made some comments in the code, and this here we can remove because instead I put the comments in the code. So let's go down and see. Let me just complete this comment. If you remember, the Gaussians are defined this way. The first part in it is the constant in front. The second is the constant in the exponential with a minus. And then the third is, that should be times. And the third is going to be, I could say x or whatever variable it is, x minus, and this would be par init 3. And that's squared. And then the second Gaussian is the next three parameters, and so on. All right, so remember, when you're trying to convert Gaussians, the par inits, you have three parameters for each Gaussian, and the parameters match up this way. You can verify that by looking in the Gauss function here, not this one, but the small g fun. Here we don't put the a of 1 here, but here you have the a of 2 and the a of 3. All right, so that's fine. And so let's go back here. Now, what you want to do here is use your int-select fun. Previously, we did this manually. Now you're going to use your int-select fun. And you should make sure that your int-select fun gives you something that makes sense. Now, to do int-select fun, you're going to remember what you're trying to do. You're trying to find the values of h that are close to the peaks. And you can use, what did we call it? I think we call it cutoff. You can use cutoff equals 0.9, that's fine. That's perfectly fine. All right. So you're going to be using this. I don't know if we call it H yet. I think we call it smooth data. Let me make sure. I think, yeah, we're going to be using smooth data. Okay. So, and this is going to be on smooth data. And it's smooth data of IX. So you can just, actually it's just on temp2 up here. So you can use that function on temp2. Right? So on temp2. And that will give you your, that will give you, or why don't I just do it this way, because that's what we've used down here. I'll just say this is on smooth data. It would be good to do it this way, I think. It's going to be the IX column of smooth data. All right? And so you won't use these values anymore. We'll use the values that you come up with. But the value should be something similar to this. You can plot your function and your remaining function and see if this makes sense. All right, now, some things that need to fix here. Here we have skip index, and this means we only select certain values from the function. Okay, and this we can see every skip index. Okay, so this is to reduce the computation in the maximization or minimization. Okay, so that's what we're doing here. So we no longer have the same number of entries that we're using. Let's see. So here we have, for instance, if we had min index is 150, max index is 276, that would be 120, I guess 127, or 126, 127, I'm not sure. 127, I think, 127 values. But now you're only selecting every two. So here I'm going to, so what we have to do is we have to do the rescaling because we no longer have an interval of the same size. So it's convenient to define nj as length of j. And I think that we don't need h at this point. Now, one thing that I didn't do in the previous code was keep track of the frequencies. And we should do that. The frequency was defined as v. And now we're selecting some of the v's, so we should make sure to select the correct frequencies. This is vtemp, so we'll use this later. Okay. Now, the paranet was, I think that what was supposed to be here is h is equal to h of j. This is so well. It's actually not h anymore. Do I have an h here yet? I don't think so. Well, we're selecting from we're selecting from this variable. Where is it? This variable, the one I just had. Let's see if I can locate it. All right, it's the variable here, smooth data ix. Now, what I'm thinking is that let's just go ahead and make that h because we use it so much. So I'm going to, I'll change it later. Sorry, change my mind. Okay. So here, this is going to be smooth data ix. And I'm going to take j out of that. So I'm going to take only those indices. All right. So this is the selected function that needs to be fit. Okay, this is a reduced set of indices. Okay, and this is the number of the reduced set of indices. Okay, all right, so now I have my new function that I want to fit. Now remember, we tried to fit Gaussians using the second derivative of our original smooth function. But now h has changed. There's a rescaling. So we'll have to use your rescale function. Now these are the new frequencies. We'll keep that in back of our mind. But this is what you have to. This is what you're going to have to do. Right? And then here, I'll put this here also. You want to do this here. Right. And you should make sure that you check that your values make sense. So, so you need to change paranet based on this new transformation. Okay. So now the index min index has been mapped to 1, and the index j of nj has been mapped to nj. Okay. Because now my first h here corresponds to the first value of j, but j starts with min index. Okay. Okay. So min index has now become 1, and the last index here, the last index in j has become nj because I've mapped this to a set of integers. Okay. All right. So you need to choose B and C to rescale this paranet accordingly using the rescale Gauss function. All right. Okay, so in your rescaling, you choose B and C to map this interval min index j of nj, you map that interval to the interval 1 nj. So you can choose B and C that will accomplish that mapping. So linear function that maps min index to 1 and j of nj to nj. So that you can use that to solve B and C. You can also use A equals 1 over max of h, so the maximum value is 1. Okay, and you should rescale h also by that value. Or just multiply h also by that value. Okay, because we want to put everything, all the functions that we have, between 0 and 1. Right? So we can do that stuff. Right. Now finally we have one more rescaling, which was the original reason why I had rescale fun. Right now we have our h has indices running from 1 to nj. And our Gaussian function also has indices running from 1 to nj, right? Because that's the new interval. But I want to map that to 0 to 1 in order to standardize all the sizes of all the variables. Now you do this rescaling, but you don't change the function value. Okay? So you're going to map 1 to 0 and nj to 1. So you choose B and C accordingly. Now, you will need to use rescale. You need to rescale h and j to these values using rescale fun. Okay, and you'll use this B and C in order to do the rescaling, but you can have a equals 1. So we're trying to get everything in the interval from 0 to 1 and have the function heights so they also run from 0 to 1. Okay. At this point, we're going to use these new values as constants. Right. You'll also need to rescale your power net again in the same way. So this is using the same B and C. Okay. All right, now you can verify your rescaling by plotting h as a function of j. So j would be the x values, h are the y values. And also you want to plot this Gaussian function using the parameters also as a function of j. Okay. And the Gaussian function should line up with h and be roughly the same size. Okay. Notice that j here is no longer a set of integers because we're scaling it so that the values of j lie between 0 and 1. Right. So I know this may be challenging. Try to keep in mind what we're trying to do. We're trying to scale both the function and the Gaussian. The domain is from 0 to 1, and the range is also from 0 to 1. And we do several operations here. First, we truncate according to min index, max index. And then we select, like in this case, we'd select every second value. So this involves a rescaling, essentially, of the x-axis. Instead of the x values running from 150 to 276, they now run from 0 to the length of j. Right, so that's one rescaling. So we do that. And then another rescaling is we try to map those numbers to the interval 0 to 1. So there's a second rescaling. So the shape of the function should not change. Basically just the x values and also the scale on the y as well. Right, so that's kind of how this works. See where you can get with that, and we'll talk on the weekend.